For his creative ideas, he was awarded the prize, the New Horizons Prize of the Breakthrough Foundation. And in this honor, he shared together with two of his intellectual siblings, Mina and Peter, both of which will be here in a short while. So today he's going to talk to us about something very different, and it will be causal framework for nonlinear quantum mechanics.
All right, thank you very much. It's a pleasure to be officially invited to Stanford. So this is, let me see what's going on here. Okay. Why does one want to modify quantum mechanics, right? Of course, quantum mechanics is a fundamental theory of nature. So why would one want to go and modify it? So if we think about quantum mechanics, right, it's not like the rules of quantum mechanics were discovered by some guy written in a golden tablet in some cave in a mountain. If that's how quantum mechanics was discovered, we would of course think that those rules are absolutely accurate and that's how we should organize society. That's not how we discovered quantum mechanics. The way quantum mechanics was actually discovered was that the rules of quantum mechanics were discovered was that a bunch of people got together in a conference and looked at a bunch of data and said, look, these are the rules of nature, right? So why should it be that a group of people coming together in a conference come up with the absolute truth that could never be changed? Why should that be true? We should question it. So if you think about modifying quantum mechanics, you can ask there are two main postulates of quantum mechanics, and which of these postulates should we want to modify? So the two fundamental postulates are basically that probability is a fundamental part of the description of nature. And the second is that the time evolution of quantum systems is linear. Which of these two things should one try to alter? And how might one go about doing it? The first thing is probability. There's been a lot of work in trying to eliminate probability from quantum mechanics. And in my opinion, that's a waste of time. And I'll tell you why. So why is it that we have probability in the laws of nature? Why is that a fundamental aspect of it? And that is really because of two experimental facts about the world. The first is that if you actually take some kind of a finite system, like a hydrogen atom, something like this, and you fix some energy level, and you basically ask, how many states do I have below a fixed energy? It's a finite number of them. That's a fact about the world, right? The hydrogen has a discrete spectrum of some kind. Secondly, the world also has continuous observables and symmetries. Let me point out to you that these two facts are in contradiction to the assumption that every observable of the system is always deterministic. Why? Let's ask this question. If I have an electron in an atom, could the electron actually have a well-defined position at all times? So when I was a child, my picture of the electron in an atom was that the electron was a little dot going around the atom, like the proton, like the solar system, right? So if you take this picture of the atom, that's what I thought the atom was like. But suppose that was actually true, right? So what that means is that we would say that the electron going around the proton has a well-defined position and it has a well-defined energy, okay? Suppose that was true, now we can make use of the fact that we actually have rotations in the world. So if you take this particular system, I hope this actually works. It works. It works?
Yeah, it was there.
Oh, it's there? Okay. Wait, what? I don't actually see it at all. Oh, this is completely useless. It doesn't show up there. Okay.
I have a red one also.
You have a red one, that may be useful. Yes. This is yeah, that's better. That's better. Thank you. Yeah, yeah. I was suddenly being an idiot and suddenly, not able to use a pointer. Great. Okay. So if you now take this system where the electron has a well-defined position around the proton and you apply a rotation, you're going to get another state where the electron has another well-defined position around the proton. So both of these were allowed states of the system. Because I can apply an arbitrary rotation, I essentially end up getting a continuous infinity of states, all of them at the same energy. And that, of course, contradicts my assumption that the state only has a finite number of sets of energies below a given energy level, right? So you cannot actually have the electron having a well-defined position if you actually believed both of these facts about the world. So there has to be something probabilistic. And that is essentially what quantum mechanics is doing. Quantum mechanics is a compromise. It basically says that I'm going to sacrifice absolute determinism in order to preserve a finite set of energy states in my system while still allowing for continuous symmetries and observables. So if you look at various tests of quantum mechanics, such as the Bell inequalities, the Koch-Specker theorems, and I think the SSC theorems is what is out there that's cut off. All of these are fundamentally making use of this contradiction between the fact that I have a finite set of energy levels and a small number of deterministic observables. So if you think about the Bell inequalities, what they're basically doing is that they look for various kinds of angular momentum states. And obviously, there are only a finite number of angular momentum states in the world for below something. But I can measure rotation in multiple different angles. And so essentially, if you measure rotation enough times on a finite set of angular momentum states, there will be a contradiction between the classical assumption that the angular momentum is well defined in every direction versus what quantum mechanics tells you, which is that one can only have angular momentum well defined along certain axes, right? That is the basic idea behind all of these proofs. And essentially, these two facts tell you that if you're trying to eliminate probability from your description of the world, you're wasting your time. What about linearity? Linearity, the basic idea is that the wave function does not interact with itself in quantum mechanics. What does it actually mean? It basically means that if I take the hydrogen atom and I have the 2s and 2p levels of hydrogen, right? The 2s and 2p levels of hydrogen in quantum mechanics have exactly the same energy, essentially up to the corrections from QED. And if you think about that for a second, it's a little weird, right? Because the 2s is some kind of a spherical shell, a spherical ball, I guess, and the 2p is some kind of a dumbbell. And if you naively thought of quantum mechanical self-energies as a statement that there's some charge density, you would think that if I have a spherical ball versus a dumbbell, the self-energy contributions to the state would be different, whether you're a sphere or a dumbbell. That clearly doesn't exist, and that is because of the fact that the electron doesn't talk to itself in hydrogen. That's what linearity practically means in this case. But it's not like there is some deep reason why the shape of the electron cloud should be hidden. Because if I put a second, what's happening here? If I put a second charged particle, right? The second charged particle is obviously sensitive to the shape of the electron cloud. So for example, the 2s electron will see more of a screening on this side than the 2p on this side. Okay, so it's not like there is some deep reason in nature why the shape of the electron cloud cannot be visible in quantum mechanics. It obviously is. So what if we try to make the electron talk to itself, the wave function talk to itself, try to make the evolution nonlinear? What are the issues? The main issue you may run into is causality. And then one also has to think about whether or not you can actually have a sensible theory of measurement in the story. And really, at the end of the day, since everything depends upon quantum field theory, you have to ask, if I take a nonlinear quantum mechanical system like this, is it possible for me to incorporate that into field theory? Why is causality an issue in the first place? So let me first do something and tell you what's wrong with it. So let me write down a trial nonlinear term. So I'm writing this term I d psi dt, the Schrodinger equation-like thing. This is a linear part of the Hamiltonian. And nonlinear means I'm going to have the state affect itself in this time evolution. So let me write down a dumb term, epsilon psi squared plus psi star squared. Psi star is the complex conjugate of psi. And that's a nonlinear equation. At a single particle level, nothing goes wrong, right? This is some complicated differential equation. You can go solve it. You get whatever you get and be happy. But the crucial issue in quantum mechanics is that it is in fact the case that entanglement is a fundamental part of quantum mechanics because I have multi-particle systems, and multi-particle systems can easily be entangled with each other. So now think about what would happen if I took this as my trial equation for time evolution. If I take this entangled state, right, I can now do the following thing. I can take two systems labeled as alpha I and beta j at coordinates x and y, come close to each other, create this entangled state, and then keep one system near me and take the other system and go a very long distance away, go to Mars. All right. And now if you write down this nonlinear time evolution, you can now worry about the following thing. What would happen if I went to Mars and I did a local operation on the particle in Mars, right? So that's my particle at y. So applying a local operation simply means that I'm going to change the coefficients of this expectation, of this state here, because I did some rotation. Okay. If you have a term like psi squared and psi star squared, like the way I wrote it down, you can convince yourself that what's going to happen is that when you make a local operation on this particular particle, that will change these coefficients, and those coefficients will now affect how the particle at x is evolving immediately. Okay, and that basically means you have violated causality because you can go to Mars and make a little change, and immediately affect how the particle on the Earth is evolving. All right. So if you know some of the history, Weinberg tried to come up with a nonlinear modification of quantum mechanics, and this is what he messed up. He wrote down a theory that was not causal when you were trying to describe more than one particle. And of course, since Weinberg failed, everybody assumed you could never do it. But it's not like nonlinearity is somehow a fundamentally acausal thing, right? We know plenty of examples of causal theories in the world that are nonlinear. And if you take a typical classical field theory and it has nonlinear interactions, and you ask, how is it that these nonlinear theories that are in classical physics maintain causality? It's really because at the end of the day, causality is enforced by some kind of a Green's function, right? I shake something, whatever I'm shaking, if its effect has to be felt far away, it's got to go through some Green's function. And it's these Green's functions that at the end of the day maintain causality. Now comes the interesting set of ideas, in my opinion. Linear quantum mechanics is, of course, basis independent. You don't care which basis you write down linear quantum mechanics in. That's totally fine. But there is a fact about the world, which is that if you think about what kind of Hamiltonians we have in the world, the Hamiltonians we have in the world are all local. They care about position, right? So quantum field theory is naturally something that you talk about in the position basis. And if you care about causality, you obviously care about X. So instead of trying to formulate a nonlinear theory of quantum mechanics in a basis independent way, which is what Weinberg was trying to do, I'm going to be like, look, the problem you're dealing with is actually causality. So instead of trying to write down a most general framework for nonlinear quantum mechanics, let me try to figure out what can I do in a position basis, which is based upon field theory. Secondly, if you think about it, I learned this from Weinberg's own book. The reason why you use quantum field theory is because quantum field theory is the most natural way to incorporate causality in multi-particle systems, right? That's one of the basic ideas of quantum field theory. That's one of the reasons why we use it all the time. So here comes an interesting philosophical difference. Normally, when we think about quantum field theory, right, we think of quantum field theory as being a subset of quantum mechanics. Quantum mechanics is a much broader set of ideas, and we say, look, quantum field theory is an application of quantum mechanics for continuous systems. That's basically how we learn it. But I'm going to take the point of view that if I look at the problems with nonlinear quantum mechanics that Weinberg faced, those are all about causality. So I need to care about position. I need to care about multi-particle systems. Quantum field theory is the most natural way to deal with all of these problems. So I'm going to directly go and figure out if I can introduce nonlinearities in quantum mechanics into field theory itself. And that is generally a good thing to do because of the fact that we, at the end of the day, care about quantum field theory because it's field theory that ultimately tells us what's going on in the world. So we will completely be in field theory in the full picture. So here is the outline for my talk. I will describe the framework where we talk about how we introduce these nonlinear evolution field theory, describe the one particle Schrodinger picture, talk about issues of causality and measurement. Nonlinear quantum mechanics will turn out to have some really interesting macroscopic effects. And those will be some of the most wildest things you'll hear me say today. And then we'll talk about how constrained nonlinear quantum mechanics actually is. It is much less constrained than you might think it is. And then talk about ongoing experimental efforts that I've managed to motivate some people to do. And then we'll talk about the fact that these nonlinear quantum mechanical effects are extremely sensitive to cosmology in some crazy ways. And then I'll conclude. Here's the framework. So let me give you a very brief overview of quantum field theory and how this thing is actually going to work. So this is a so-called Schrodinger picture of quantum field theory. And the Schrodinger picture of quantum field theory, here's what you're doing. There is a wave functional. It's just a state. It's just a column vector of states. And that's called a Fock state or something. Okay, it's basically the state of all quantum fields. And then you have some operators, which are the fields, the quantum fields. So, okay, that's basically what it is. All you have to know is basically that these are operators and these are states. And you time evolve the whole states by using a Hamiltonian. The Hamiltonian is a function of these operators. So even in quantum field theory, what you're actually doing is that you're simply solving Schrodinger's equation, I d chi dt equal to h chi. The Hamiltonian is now a function of these operators. The chi are simply quantum states. That's all you're actually doing. Notice that this particular equation can be obtained by the following idea. So this is not the usual action that one writes down in quantum field theory. I'm just making up this action simply because it helps me introduce a nonlinearity in a natural way. Okay, so notice that if I look at this particular action, all right, so this is the quantum state chi, and this is the Hamiltonian operator. I can look at this action and insist that the equation of motion of the world is the action that minimizes this particular, is the path, if you will, that minimizes this particular action in some Hilbert space. That's just something I made up. If I do that, you can pretty much easily see that the Euler-Lagrange equation for this gives you Schrodinger's equation. So I would say that basically, yes, I can derive this Schrodinger evolution simply by minimizing this particular action. In QFT, you don't do this because it doesn't actually buy you anything, but here it will. So let's think about what happens for a Yukawa theory, okay? Which is a theory of a scalar interacting with a fermion. So in that case, I have a Hamiltonian, and the Hamiltonian is of this particular form. This Y is the Yukawa coupling. Phi is my scalar field phi, and the psi's are basically my fermion operators. So for this discussion, all you really need to know is that these are all operators, some matrices living in there. So let me write down the usual action that I just wrote down. So this is the action that I like to write, chi dot times this Hamiltonian here. And all I'm going to do is plug in for what this particular interaction term looks like in the Hamiltonian, and that gives me this particular term. So all I have done is this chi h chi contains chi phi of x, psi bar of x, psi of x chi, right? So what's going on here is that I've basically got a set of matrices or operators, and I'm taking an expectation value, which is simply converting these operators into some number. And I can move, obviously, this chi of t inside because there's no time integral here. So essentially, this Yukawa theory is described by this particular kind of term existing in the action, this particular action. For the last 100 years, we have been studying a variety of quantum field theories, which essentially involve taking these kinds of operators and adding higher order terms. So this is regular quantum field theory, where we make the action nonlinear in the operators. Okay, this is normal quantum field theory, and we think all of that is very sensible, right? We build experiments, do all these kinds of things to see if these operators exist. That is essentially all of BSM physics. And these are, of course, nonlinearities in the operators, but not in the states, right? I have only two chi's appearing in here, but many, many copies of the phi's and the psi's. Great. But if you look at this particular expression, you have to ask yourself, what do I need in the action? All I need in the action is that I need the action to be a number. And the whole point of making the action a number is a statement that I have a bunch of operators, and then I have a couple of vectors, and I'm using these operators to convert those, using the vectors to convert the operators into a number. That's it. There's a very natural thing I can do now, where I can observe there's another way for me to get a number here, where basically I take one of these operators, right, chi of t, phi of x, psi bar of x, whatever, and I can insert states in the middle. So for example, I can look at this guy and be inspired to write down this particular term. This is my nonlinear term, right? Where essentially what I'm doing is I'm taking the expectation value of the phi of x operator and the expectation value of the psi bar psi. That's, again, all I've done is I've taken a matrix, two vectors gives me a number, a matrix, two vectors gives me a number. That's a very reasonable thing to write down. That's my entire theory. That's the entire framework. If you think about it, this obeys all the standard rules, right? This is some Lorentz invariant thing that you can write down. And what it means over here is that this, of course, leads to time evolution that will depend on higher order in the states and not just in the operators. Okay, that's the basic idea. So this leads to state-dependent time evolution. And I'm a perturbative guy, so we can just think about what's going to happen in this theory perturbatively. Right? So I'm going to understand this entire theory as a perturbation theory in epsilon. How does that look like, for example, for the Yukawa theory? What does this mean? So if I go through the Euler-Lagrange procedure to figure out what the equation of motion is, unsurprisingly, what happens is that this term that used to be the normal Yukawa coupling term now contains two things. There's a y phi psi bar psi. That's the usual Yukawa interaction that you already had. And the expectation value term that I put in there gives this extra piece, epsilon chi phi chi. That's it. Right? That's what you get from the Euler-Lagrange procedure. And my claim is basically that, look, I can now time evolve the system exactly like I used to do it before. I d chi dt equal to h chi is that h now depends upon this term as well. So there is a nonlinear state-dependent term in the evolution. So how do I do this in perturbation theory? In perturbation theory, what I'm going to do is I'm going to basically figure this out by first saying Well, let me compute the zeroth order revolution. The zeroth order revolution, of course, is just standard quantum field theory, nothing dramatic going on. So now I want to compute the first order nonlinear correction. The first order nonlinear correction, all I need to do is basically use the zeroth order solution, okay, where essentially I will use my quantum field theory normally to just compute this expectation value. I'll plug that into these equations, because I just need to know that to zeroth order to compute the first order correction. And once I have known what that zeroth order term is, I put that in, I can now compute the first order correction. That's how you do perturbation theory. So it's very easy at this point to see why this procedure will only give you causal evolution, because of a very simple fact. This guy, the expectation value of phi on this state, remember I'm first calculating that using quantum field theory. That quantity is an observable of quantum field theory. And because there's an observable of quantum field theory, that quantity is always causal. No matter what you do, you take two systems, you entangle them, move around, do whatever you want. You compute this quantity, that quantity is always be causal. Because if it's not causal, you've got a bigger problem. And you can explicitly verify that that term is causal. Once the zeroth order term there is causal, if you want to first compute what the first order time evolution looks like, this term appears in your equation of motion simply as a background classical field. Now we know how to do the quantum mechanics of that, right? We've been doing something called the semi-classical approximation all the time in when you do quantum mechanics, where we simply say, look, there's some part of your dynamics that you think is classical, you just put it in the background field and do time evolution on top of that. That will never give you anything acausal, because all of the thing that is leading up to it is causal, and the time evolution on top of that is also causal. So perturbatively, it's very clear that in this particular framework, you're not going to get anything bizarre happening, simply because you're building everything on top of causal quantum field theory, and everything else is perturbatively built on top of that using standard causal arguments. So that is the fundamental reason why this story always maintains causality. What does the single particle picture look like, right? So I'm interested now in what the fermion psi will see. And essentially, we're just taking a particle psi, it's a fermion, it's coupled to the scalar field phi. And I'm interested in asking what is the Schrodinger equation for a single particle. Okay, I've kind of done the opposite thing, right? Normally, you write down the single particle equation and then jump into the multi-particle field theory. Now we're saying, look, the field theory is the correct thing. And now I'm going to write down what the single particle thing looks like. So how does the single particle thing evolve? Well, again, in perturbation theory, all you're going to do is basically say at zeroth order, if I want to understand what the first order correction looks like, just go and compute what this expectation value looks like. And at zeroth order, we know what happens. The fermion psi simply sources this field phi, right? This sort of Yukawa field phi. And you can just do a straightforward computation of the expectation value in that state. What does that look like? Well, basically, this is just the fact that if I have this fermion in some state, some wave function, this expectation value is simply the integral d4x psi star psi times some Green's function, right? This is basically the statement that if I have some distribution of the psi particle here, this expectation value is just computing some kind of potential around it. That's it. Very straightforward. So you end up getting this Green's function. And that's important because remember, Green's functions are how you maintain causality in pretty much any theory. So that automatically shows up here. Okay. So I'm going to take that particular Green's function that I got and plug that into the Schrodinger equation. So now if I think about a single particle time evolution, I've got I d psi dt is equal to some normal Hamiltonian that you already had. And now there is going to be this extra piece, which is this expectation value, where it's simply some charge density of psi, and there's some Green's function going around there and telling you how the system will actually evolve. So now we can compute one of the simple effects immediately, which is essentially the statement that if I have, let us say, a hydrogen atom, where the hydrogen atom say is bound by this phi particle or something, and I look at the 2s and 2p levels of hydrogen, right? You're now going to find that because I have this extra term sitting in here, and that is this nonlinear term, and that's a wave function interacting with itself, if you simply go and calculate what is the correction to the energy of 2s and 2p because of this particular self-interaction term there, you're going to find the 2s and 2p levels are no longer exactly degenerate. The degeneracy is broken by the fact that this guy is talking to itself. And you can actually go ahead and verify many other statements, things that we normally like. So this is the Hermitian form of the Hamiltonian, if you look at it. And because it's a Hermitian form, it conserves the norm, stuff like that. this whole thing is derived from some sensible action in the first place. So you can also use that to prove conservation of energy, symmetries, all those sorts of things, right? Because basically this thing is not coming from anything that different from quantum field theory in the first place. All of the standard results that you use to prove various statements about quantum field theory, you can import it directly and realize that those things are also true. So it also helps you maintain the probabilistic interpretation of quantum mechanics that's been cut off by this particular slide there. What about entangled systems, right? The thing that actually caused trouble for Weinberg. So again, the point is we're going to take some wave function of this kind that is entangled in this complicated way. And now we're going to compute what happens to multi-particle systems. I don't have to make any kind of guess, right? If I have two particles and the two particles are sourcing the phi field, I can simply go ahead and compute this expectation value for those things. And if you compute the expectation value, this is what it looks like, right? So I've got two particles. Both these particles are sourcing the phi field. And now I ask, well, how do they affect each other? Essentially, what's going to happen is that the particle at x1, okay, the thing that you're sort of computing the charge density over, that guy can talk to x and y, but it acts through a sum of Green's functions, right? Basically, I've got these two charge distributions, and you're saying, how does this charge distribution affect a particle here and a particle there? Well, of course, it's going to go with Green's function, go from here to here, Green's function, go from here to here, so on and so forth, right? That's automatically built into quantum field theory, once again, because this thing is just an observable of quantum field theory. What is very, very nice about this is that I told you that Weinberg messed this up, right? Weinberg tried to come up with nonlinear quantum mechanics. He wrote down a theory that wasn't causal. And Joe Polchinski actually told him, figured out that this was a problem. And what Polchinski did is that he actually said, look, the specific form that Weinberg wrote down is wrong, it's acausal. But look, I can actually have causal evolution if the way in which nonlinearity for multi-particle states is in this additive form. So he didn't write down the Green's function. What he basically said that if you have two systems A and B, and they're entangled in some way, and they want to time evolve, as long as it is the case that the nonlinearity acts additively, right? Like system A plus system B, he was able to show that would actually be causal. That was the main result of his paper. You can see this is exactly what happens here, right? The way system A affects system B or system A affects itself, they're all adding with each other, this additive form. And what you see is that the additive form demanded by Polchinski from very general arguments naturally comes out of field theory. Let's talk about measurement in quantum mechanics. So this is the part where I tend to typically lose about half my audience, simply because of the fact that a good number of people do not actually understand measurement in quantum mechanics. You've been told that measurement is a puzzle. There's a whole bunch of people who sit and work on the measurement problem. The problem of measurement in quantum mechanics was actually well understood in the 1950s by Everett. And I'm going to simply tell you what the understanding actually is. What is measurement in quantum mechanics? It's not some mysterious process, right? Measurement is simply the statement that you take two systems. One is your quantum system, and the other is some measuring device. The measuring device, of course, is not some mysterious object. It's made of atoms. It also obeys quantum mechanical evolution, right? You bring these two guys together, and what you actually do during a measurement, of course, is to bring them together, and you allow them to time evolve using the Schrodinger equation. If you do that, you're going to find that in general, right, this system will evolve into a complicated mess of entangled states. That is a prediction of quantum mechanics. It is not some interpretation. It is what actually happens if you believe in quantum mechanics. Some people don't like it. That's fine, right? It's a free country. You can like whatever you want. But the main point is that if you don't think this is what happens, you are already going beyond quantum mechanics. You're already going beyond unitary time evolution. You're going beyond standard Schrodinger evolution. It's then upon you to come up with a sensible way to describe the phenomena of measurement, and I will bet against you. Okay, we can talk about why I make that bet, but this much is provable, that essentially, as long as you admit that measurement is nothing but the interaction of quantum systems via a Hamiltonian, this is a prediction of quantum mechanics. It just gets a stupid name called the many worlds interpretation of quantum mechanics, which makes people think it's kind of weird. In my opinion, it should be called the Princeton interpretation of quantum mechanics, and then everybody would take it very seriously. All right. So what do we actually do when we actually make a measurement? Really, is a statement that you basically take some measuring device that's initially in some initial state, and then you pick the Hamiltonian, which says that, look, if I got spin up I'm going to choose some state of my measuring device to go that way. If I got spin down, I'm going to choose some state of the measuring device to go the other way. That's basically what you're doing, because you're coming up with a Hamiltonian which helps you make an understanding of what's actually going on. So typically, to get a good measurement, what you do is that you choose your Hamiltonian so that the states AI and AJ are orthogonal to each other. And when that is the case, if you look at this complicated entangled state that you got, you can prove to yourself that as long as I'm not able to do anything to this macroscopic state in general, if I'm only focusing myself on this quantum state, then all of the subsequent time evolution of the system is simply described by this reduced density matrix, in which case this can simply become a direct sum of probabilities. That's basically what you learn. Okay, that the moment this is a complicated entangled state and I can't mess with this anymore because it's too big, essentially this thing acts like the collapse of the wave function. Okay, but the key point is that in this many worlds or this principal interpretation of quantum mechanics, the moment you create this entanglement, this entire state exists. It's not like some state drops off. What about nonlinear quantum mechanics? I'm not going to change anything at all from the standard idea. I'm basically going to say measurement in my story also continues to be an interaction between a quantum state and a measuring device, right? So I'm going to basically take my quantum state, entangle it with a measuring device, and I'm going to simply calculate the time evolution and get whatever I get. Yes.
The entire state exists.
Yes.
What does exist mean in this one? Are you talking about what you can measure? What you argue would be?
I'm talking about the fact that if I take this quantum system, initial quantum system, and do time evolution, the time evolution predicts that that is the answer. That's a calculation. Yeah. All right. So here is the key difference, okay, that's going to come up between linear quantum mechanics and nonlinear quantum mechanics. Because in linear quantum mechanics, if I want to create a good measuring device, I don't have to know anything about the state. My whole purpose is to discover what the state actually is. So all I need to know about linear quantum mechanics is that if I want to measure a state, I need to know the basis vectors of my quantum system, with spin up, spin down, those basis vectors, and I need to know the basis vectors of my measuring device. As long as I know the basis vectors, I can design a Hamiltonian that will give me the answer that I want, right? And the answer I want, of course, is that I want these states to be orthogonal to each other when they get entangled this way. In nonlinear quantum mechanics, of course, the key point is that the time evolution depends upon the state itself. So if I gave you an unknown state, okay, since the time evolution depends upon itself, or on the state itself, I cannot guarantee that this outcome will always preserve the orthogonality between these different states. I can't guarantee that because the time evolution, of course, depends upon the state itself. So what that means in general is that in nonlinear quantum mechanics, as you allow for time evolution, you will indeed get this initial direct sum, as we talked about earlier, that's just from linear quantum mechanics, but then there'll be some thing that's cut off here again, which is essentially the fact that some of these states will be mixed with each other, right? So fundamentally, there is going to be some kind of measurement noise in the system because of the fact that I can't guarantee perfect orthogonality in time evolution.
You can hide
How do I hide that? Wait, so how do I hide this actually? I can't get my cursor out here either.
You can put more, but you don't have to.
I don't have a cursor, yeah.
Then you might.
Well, okay. Anyway, yeah. I'll make a simple comment that so far everything we've discussed is about the Yukawa theory. It's not too difficult to basically use these same ideas to also include nonlinearities in electromagnetism and gravitation, right? So all you do for electromagnetism and gravitation, it's much more reasonable to formulate these theories not in the Hamiltonian language, but rather using path integrals. And all this path integral language is basically a statement that you take the standard path integral for quantum field theory, and then to that you basically add these expectation values. And when you do the time evolution, these things are simply going to be background fields. Was that a question?
Yeah. So one of the things about quantum field theory is there's this, maybe this is a dumb question. There's this reparameterization invariance, like I can take any interpolation function that interpolates, a one particle state in the vacuum, and I can use that.
Yeah, you can do all of that here too.
How do I see that? Because I would think that like if I tried to take a different AU or different FU here, it would totally change.
You do get state dependent time evolution, right? But essentially the idea is the fact that if I'm trying to think about how the particles are being defined, all of that is really just happening at the zeroth order statement, right? So of course, once you create your particles, then if you're talking about time evolution, the time evolution depends upon the state itself. Absolutely. I mean, that's the whole point of it being nonlinear. One can also similarly do this with gravitation, where you simply just add expectation values to the metric in the path integral for gravity. And that's again something you can sensibly do. So now we're going to move to the kind of macroscopic effects of quantum mechanics. And this is the part where people will be like, oh, poor Surjeet. The guy went crazy during the pandemic, right? And what I'll point out is that in my defense, I've been crazy a long time. The pandemic had nothing to do with it. I'm also not the craziest person to be associated with this ITP, okay? But yes, Shaman.
I have a sort of vague question, but it's important conceptually.
Yeah.
You've written quantum field theories in a very perturbative language. There's an F, then there's a phi, and there's a psi.
Yes.
The modern way of thinking about quantum field theory abstractly, we have like launching local operators.
Sure.
And we don't think about the local operators as strings of perturbative fields that get dressed up. There's local operators.
Yes.
So if you wrote the quantum field theory that way, your convention for breaking it up into little bits that are sandwiched between phis, what are you doing there? I mean, you have local operators, you write phi O phi for every operator, but then you just have one copy of sort of pi O pi everywhere.
No, so if you go back to the action that I wrote down in the very beginning, let's go to that one, right? That's the Hamiltonian picture. There, let's ask that question, right? So you would simply say, yeah, I mean, like a quantum field theory is a combination of both operators and states. If you're simply thinking about the theory as only a theory of linear quantum mechanics, you can pretty much ignore the state. You can just put it as a function of operators alone. I would claim that it's just something that you're conveniently used to thinking about because you're used to linearity. But I would say in general, quantum mechanics is a story about how the states evolve. And for me, that's a combination of how states and operators evolve together. And so I can take my initial polynomial in the operators that I wrote down and sandwich different states there.
By breaking the operators up in some abstract way into smaller operators, because you know.
I mean, phi of x isn't, yeah, sure, yeah.
There are no phi's and psi's, right? There's just local operators. So
sure.
You made a very large number of arbitrary choices. I'm kind of confused how you phrase it.
Well, I mean, I'm a perturbative guy, right? So at the end of the day, if I look at quantum field theory, there's a Yukawa coupling, there is phi of x and psi. And you know, this could very well just be some philosophical question. And I would simply say that I'm happy with the Yukawa theory, the world is whatever it is. I'm simply making this thing that essentially I can put an expectation value around phi, which is very different to me from what the fermions are. So you can ask this question like, how did I know how to parcel off phi or psi in this complicated way? And you know, I mean, I'm looking at it from a very effective theory point of view, where the world gives me these things. Look, I can do this. I'm not a philosopher.
You're also not a field theorist, apparently.
Well, if you can point out a specific reason why that's wrong, I would be happy to know, but you have not done that.
Well, I'm just saying, phrase this in a CFT. And I don't think you answer the question. It's a reasonable question. You don't have to answer.
Well, I mean, yes, if it's a very complicated CFT, I don't exactly know how you would parcel this off. But I think certainly in these kinds of theories, I've not studied those specific kinds of examples. But in this particular theory, it's pretty clear what we're doing.
Like lower order thought question on this, which is when you call it theory, there's no problem with this, but if you were doing like 5-4 theory, for example,
yeah,
you split it up in some way, do you not have some weird issue with normal ordering versus time ordering?
Not really. Look, the thing is, at the end of the day, you're just taking an expectation value of a field. Is that a well-defined thing?
Yes, but you probably want that to be normal order or something.
Yeah, I mean, so it's a question of whether or not you want to write this in the Hamiltonian language or the path integral language. The path integral has the benefit that one doesn't have to worry about things of that kind, right? So in the Hamiltonian, yes, I would say the Hamiltonian is something where intrinsically it only makes sense, in my opinion, if it's normal ordered. And once it's normal ordered, it's indeed the case that you just take a path integral that's normal ordered, and then you take expectation values of whatever you want. But in the path integral, one doesn't have to worry about that ever. You just simply say, yes, given this particular path integral, I can think about this observable, there's an observable of quantum field theory, which is its expectation value. I can put that in. So what are the macroscopic effects that one worries about or happens in this particular story, right? So essentially, let's say I take the following simple experiment. Suppose I take a spin and the spin is along the x direction, okay? And I'm an experimentalist. And then with me, I've got some equipment like a laser and I've got 2 photodetectors. The initial state of the world is the fact that I've got some, that contains all these things, right? I want this initial state to be basically the spin along x direction, the experimentalist, and the laser, and all these kinds of things. My goal is that I want to create a macroscopic superposition. I'm not trying to create a coherent macroscopic superposition. I just want to simply create a macroscopic superposition. And that's very easy to do. All I'm going to do is I'm going to measure the spin along the y direction. And depending upon the outcome of that measurement, I'm going to do one of two things. If I got spin up, I'm going to send the laser to the top. If I get spin down, I'm going to send the laser to the right. Okay, a very simple macroscopic choice. So that's the idea. Measure spin along x. You know, I'm going to get measures. I mean, sorry, if I got spin, my spin outcome along y, I'm going to get spin going up there, and then I'm sending my laser to the top. If I get spin down, I'm going to send the laser to the right. So again, this thing got cut off. It's annoying. What full quantum state you get in this story, I'll just say out what it is basically that when you make this measurement, you're going to end up getting a superposition of states, which is basically spin went up, the laser went to the top, and it got entangled with some environment to the top. Plus, the spin went down, the laser went to the right, and it got entangled with the environment also to the right. Both those states exist. That's a prediction of quantum mechanics. And now one can ask this question: which of these photodetectors actually sort of light up in this particular story, right? So in linear quantum mechanics, what happens, of course, is basically that if I am entangled with this world where the spin came up and the laser went to the top, obviously we know the answer. This one lights up, and the spin got down, this thing lights up. That is fundamentally because of the fact that I am ultimately having some electrons here and here, and these electrons are reacting to the value of the electromagnetic field at the top or to the right. And essentially what you learn is that if your spin went up because of the specific way you created this particular state, the electromagnetic field at this particular point is 0. So that's why you don't actually create like any interaction here. That photodetector remains dark. But notice that if I am simply interested in computing the expectation value of the electromagnetic field, no matter what the environment state is, whether it's the top or the bottom, since I'm using the full quantum state to calculate this expectation value, no matter what the environment is, the expectation value is non-zero in both these cases. So whether I got spin to the top or spin to the bottom, since both these states exist, that's a prediction of quantum mechanics, it is in fact the case that the expectation value of A mu, the electromagnetic field, is non-zero over here and over here, simply because in this case it is non-zero because from this world there was some electromagnetic field over there, right? That's just a simple calculation. So in nonlinear quantum mechanics, what you end up having is that since I'm putting this expectation value in there, right? There's a psi bar, gamma mu, whatever, sorry, this particular term sitting in there, there's now a state dependent expectation value that lives out there. What you basically see is that in both these worlds, okay, whatever environment you actually have, you end up getting the fact that this expectation value is non-zero. So there is some non-zero electromagnetic field both at the top and the bottom in this particular case. So what that means is that you have spin up, the laser goes to the top, that thing is going to get hot as you expect it to. But since the electromagnetic field's expectation value is non-zero, and now at order epsilon, I can actually sense this particular expectation value being non-zero, I'm going to have this photodetector light up with order epsilon. So this again is something that Polchinski realized, that if you actually come up with a causal theory of nonlinear quantum mechanics, you would end up getting communication between these different worlds. He called that the Everett phone, right? What's happening really is that I created this complicated quantum state, this elaborate superposition, and now I'm actually able to talk to these different worlds. That's of course very weird. It's not normally what we're used to, but there's nothing fundamentally logically wrong with it. It's of course weird, but it's not logically a problem. So again, you kind of see something interesting, which is that whatever it is that Polchinski figured out from very general arguments fits in very sensibly in this field theory framework and gives you exactly what he said it should give you, which is there's both causality as well as communication between these different worlds. Let's now switch and talk about constraints. Yes?
On this example, so let's say I did this with just one photon. I say my laser is going to shoot one photon to the right or one photon up. So I'm doing this particle.
If it's a one photon, is it a coherent state or not?
So no.
Then the expectation value is 0.
I see. Okay. So this is, I understand. Okay. And then question 2 on this. So let's say now I'm doing your experiment you described is a coherent state. So I do have an expectation value. What is the interpretation of energy transfer in the system? Am I just not, do I not conserve?
There's overall energy conserved in the full quantum state.
Right, but any individual.
Yeah, because the worlds are interacting with each other.
I don't visibly conserve it.
Exactly, not in any individual world. It's just that the overall quantum state, you can define a conserved energy function for the full quantum state.
Okay.
Yeah, good. Constraints. This is very important because many people have this opinion that quantum mechanics is very constrained. We've done lots of tests. We've tested certain aspects of quantum mechanics very well, which is basically the quantum part of it, things like Bell inequalities, stuff like that. But I'll argue now that non-linearities that have been extremely poorly tested because people haven't understood some simple points about causality. So let me take you through the original example that I talked about, right, which is essentially the lamp shift, the thing that motivated some of these discussions. So I take the 2s and 2p levels of hydrogen, and it is in fact the case that if I take the proton and fix it at a given location, right, and I go ahead and compute the self-interaction between the 2s and 2p levels, then there will be this large shift to the lamp shift, right? It's exactly what we actually showed. There will be this big level splitting. But here is an incredibly important fact about nonlinear quantum mechanics. When you think about the hydrogen atom and you're thinking about its energy levels, right? In linear quantum mechanics, the usual stuff, think about how you solve that problem. You basically say, if you want to find the energy levels of hydrogen, I'm going to go into the center of mass coordinates. And the center of mass coordinates, the center of mass motion decouples from the relative motion. That's how you solve the system, and the relative motion is what gives you the energy. So if you take the hydrogen atom and you look at its spatial wave function, and you make that spatial wave function localized to, let's say, an angstrom, or you spread the hydrogen atom to the size of the galaxy, it doesn't matter. The energy level will always be 13.6 eV, right? Because the center of mass motion decouples from the relative coordinate. This is not true for nonlinear quantum mechanics. In nonlinear quantum mechanics, fundamentally, if you're thinking about a causal theory, right? In a causal theory, the key point about a causal theory is that you care about the position x. And you're talking about how the wave function affects itself. So if you take this nonlinear term and you think about the hydrogen atom being localized to, say, an angstrom versus a state where the hydrogen atom is spread over the size of the galaxy, in the latter case, when you're spread over the size of the galaxy, the nonlinear term is incredibly small, right? Because the same one quantum now spread over the size of the galaxy. So if you're thinking about testing nonlinear quantum mechanics, the actual physical spread of the wave function is very important, something that you don't think about at all in linear quantum mechanics. So when many people have gone ahead and tried to do tests of nonlinear quantum mechanics using various atomic systems, they've never bothered to localize the wave function. The wave function is some trap. It's spread over some micron-sized regions, at which point many of these nonlinear effects are automatically damped, simply because the wave function is spread physically over size. So in a particular theory, if you think about it, it's even worse. So the lamp shift has been measured to 13 digits, right? And you ask, well, how is this incredibly precise lamp shift going to affect? What constraint does it put on this particular modification of nonlinear quantum mechanics? And here's the main point. In our theory, what happens is that the electron couples to the expectation value of the electromagnetic field. So let's now think about the hydrogen atom in which you're trying to measure this lamp shift. The hydrogen atom is not localized to an angstrom. It's actually spread over a micron region. So what you're supposed to do in this particular theory is that you take the hydrogen atom and you spread that over a micron distance. The expectation value of the electromagnetic field in that state is actually 0, simply because hydrogen is net neutral. Right? So the typical lamp shift experiment gives 0 bounds on this particular theory, simply because you're taking a nice neutral atom, and no matter how well you try to measure its energy levels, you won't see this nonlinearity at all. There is a bound because people have tried to measure these things with certain ions. And even there, the effect of the nonlinearity is spread out simply because the ion is not localized to a point. It's spread over some micron distance. In which case, the self-electromagnetic field it's creating is extremely small. So it turns out that the limit on epsilon is not 10 to the minus 13, 10 to the minus 14. It's basically 10 to the minus 2. Okay, so you kind of see that if you think about this thing properly in a sensible way, nonlinear quantum mechanics has been extremely poorly tested because every causal theory cares about psi of x. It cares about the position, and if you don't localize your interactions, your state, there are no bounds. So in fact, the leading constraint we can think of is actually something completely accidental. It comes from the fact that people have managed to trap ions. So if you trap an ion, okay, and say the self-interaction coupling is actually repulsive, you would say, well, if I put this thing in there, the Coulomb force will actually push this guy out. Okay, so the fact that we managed to trap ions in the case of the repulsive interaction gives an epsilon of around 10 to the minus 5. Okay, we know at least that. There is no direct limit, okay, on epsilon being attractive, because at that point you're just creating a more tightly bound ion, and one has to actually go and see how well those have been mapped. So there may be a limit out there, but there is no obvious limit from it directly. So you kind of see this, right? There's this tremendous confidence people have that nonlinear quantum mechanics is very tested. It's just not true. But here is the fact. Even though these particular ion tests that people have done and this particular Lamb shift experiments are not particularly constraining, it is not like this framework is difficult to test. It's in fact very, very easy to test in many ways. So there are a couple of kinds of experiments I'll talk about. The first is basically things where we create macroscopic superpositions. Okay, so here is the main idea. So I'm going to take a spin, for example, and determine whether it's spin up or spin down. If I get spin up, so okay, here's an apparatus. I've got a spin, I've got a magnetic field, and I've got a squid, let us say. So here's what I'm going to do. If I get spin up, I'm going to turn on the magnetic field, let's say from 10 o'clock to 10:10. Okay, dt is 10, something like that. And if I get spin off, I'm going to turn off the magnetic field from 10:10 to 10:20. If I get spin down, I'm going to turn off the magnetic field from 10 o'clock to 10:10. And if I get spin down again, I'm going to turn on the magnetic field from 10:10 to 10:20, right? Something like this. So in the linear quantum mechanical world, of course, what you're going to see is that the magnetic field, the squid will turn on between 10 o'clock and 10:10 in this case, and the spin was up, and the squid will have no magnetic field from 10:10 to 10:20. And the spin came down between 10 o'clock to 10:10, the B field is off, and from 10:10 to 10:20, it's on. But now in this particular case, right, because I have this expectation value being non-zero, it will in fact be the case that from between 10:10 and 10:20, right, the fact that in this other world I created this magnetic field will now sneak in at order epsilon. And so I'll end up seeing basically an order epsilon B magnetic field between 10:10 and 10:20. That's what your squid will measure. So that is the experiment you want to do. My friend Alex Surshkov is actually doing this in Boston, not exactly with magnetic fields initially, but just with sort of electrical things. Like he's got a little voltmeter and he's trying to communicate between the worlds doing something like this. Okay. One can also do similar tests with gravity, which I believe Jason is trying to motivate his students to do. And the idea is very simple. Depending upon the outcome of a quantum spin measurement, what you're going to do is basically take your accelerometer and either decide to move a mass close to it or far away. So if you move a mass close to your accelerometer, of course, the accelerometer will be nice and big. But what you're going to see is basically when, in the world where the mass is far away, you're going to try and see if the mass in the other world that was close to you is going to, at order epsilon, affect the acceleration. Right? It's very similar to this idea. Again, this communication between worlds. The third kind of experiment we're trying to do right now with Hartmut Hafner, yes?
Try to make serious with the many-word interpretation that we're pushing. So when is the moment when we simplify whether, like, you could follow either convention, right?
Either convention.
Yeah.
Yeah, depending upon what my outcome is, I'll do one of these two. Well, in fact, I'll do both. I am not a single person anymore, right? That's the whole point. That when I interact with the system, I've gotten entangled in this complicated way.
For example, let's say that there is a experiment that you agree superposition side. this convention or the opposite one, right? I could have
It's not either or. When you make a measurement, you get entangled, right? You get entangled with this state, plus you getting entangled with that state.
Now, my question is simple. Do I have a splitting already in the moment when I decide which convention?
Do you have a time? You have a continuous time evolution, right? So your continuous time evolution will continuously split your wave function into going this way and that way.
Yeah, I'm just saying. Let's say that I want to perform the experiment. There will be a branch of me that will follow this convention. Another will have
Yes.
follow the different convention of spin up and down switch. Also, this tool would be principle interfering, right, in the nonlinear version. So I guess I probably would need to wait enough time for the other branch to decouple enough from myself. How do I wait these different branches?
I mean, you're just doing time evolution, right? So you're basically just saying, yeah, I take the system, I'm going to get entangled in this way, and yeah, you wait for however long you want to wait to be sure that what you saw was spin up and what you saw was spin down. But very rapidly, these macroscopic systems will become completely decoherent with each other. So it's not like they're going to interfere very much, right? Because you're a macroscopic system. So very rapidly, the system will decohere. And once it's decohered to whatever level of satisfaction you want, you can then perform the experiment. So this experiment that I'm talking about is much more conventional sounding, simply because it doesn't require macroscopic superpositions interacting with each other. This is something that Hartmut, Hafner, and Berkeley is doing. And this is the idea that basically what you're going to do is that you take an ion and you split the wave function of the ion, okay, into two paths, like you normally do in some interferometer. In linear quantum mechanics, the Coulomb field of one electron does not actually interact with the other electron. Sorry, the Coulomb field of the ion doesn't talk to itself. So I take this particular wave function of the ion, I split it into two different paths, and the Coulomb field of this guy doesn't talk to itself in linear quantum mechanics. But now what you're going to find is basically the statement that because of this nonlinear term that I added in there, it'll be the case that this guy talks to the other guy, right? So you're not going to basically get a phase shift that depends upon the intensity of the splitting, right? So whether I made this 50%, 50%, or 75%, 25%, I'm now going to get a phase shift that depends upon the intensity of the split. And that's actually very useful in terms of combating systematics, because if you think about typical background electric fields and stuff like this, they don't really care about how much the splitting actually happens, right? This is the universal phase shift, but now you have an additional control because the phase shift you're looking for is intensity dependent. That's something Hartmut is actually doing at Berkeley right now. This comes to the last part of my story, which is actually very important, the cosmological sensitivity. Here is a fact about the world, right? Now, in linear quantum mechanics, one can think about the universe itself being in some superposition. I take my state chi, it is alpha times our universe, where I'm standing right now and giving you this talk, and beta times some other space-time, right? That is basically means at this point in space, x, at this point in time, I've got a completely different universe. I'm not even standing here, this is the middle of empty space. It's weird to think about, but that's actually something that's true in linear quantum mechanics. As long as you believe linear quantum mechanics and you believe in superposition, which you have to, this is an allowed state of quantum mechanics. In linear quantum mechanics, you never care about the value of alpha and beta. It's completely irrelevant, right? Because who cares whether I am a tiny part of the wave of the superposition or not? No matter what it is, I can go and time evolve my systems and get whatever, and get the standard answers. That is because in linear quantum mechanics, both the state u and alpha u for any alpha evolves exactly the same way. In nonlinear quantum mechanics, think about what we're doing. We're computing the expectation value of this guy. And the expectation value of this guy is basically alpha squared times whatever this thing is plus beta squared times whatever this thing is. So if you now think about the particular experiment we're talking about, right, where I stand somewhere and turn on a laser beam and figure out what the expectation value looks like. In the state M, which is not our world, right, at this particular point in space, at this particular point in X, I'm not standing there, I don't have a laser beam in my hand, nothing. This is the middle of empty space, who knows what, something completely different. That means all of the experiments that we're talking about, right, where I'm standing here, turning on a laser, doing all this kinds of stuff, those things only exist in our world U, they don't exist in M, right? Which means when I compute this expectation value, notice that the expectation value is simply alpha squared times this quantity, the other one doesn't contribute at all. There's no one there doing something. Which means if in the very beginning of time, whenever the universe was created, if someone decided to be mean and make alpha small, 10 to the minus 500 or whatever it is, no matter what I do today, I cannot change the value of alpha. Right? It is a fixed quantity as far as I'm concerned. Which means all of the experiments we are talking about will give you null results. Not because the theory is fundamentally linear, it's simply because of the fact that the initial state of the universe made alpha extremely tiny. That's an enormous difference between linear quantum mechanics and nonlinear quantum mechanics, because in linear quantum mechanics, you never give a damn, because alpha u and u evolve the same way, but in nonlinear quantum mechanics, the value of alpha absolutely matters. Now, so any kind of local experiment that we're talking about is completely sensitive to this value of alpha. And if alpha is just small for whatever reason, there's nothing I can actually do about it. And there's a huge difference between that and linear quantum mechanics. Okay. In fact, you can ask, could we do something to boost the effects of nonlinearity? Right? I want to make alpha bigger because I want to see these experiments work and give me something nice. What you would then have to do is basically try to take your operators and divide that by some projection operator. Right? So when you normally do linear quantum mechanics, what you actually do is the following. You basically say, yeah, there is some alpha. Okay, and I'm going to condition on the fact that I am in this universe. And the moment I condition myself on this universe, all the other crap disappears because I can just like boost my results. Of course, that's a mathematical procedure we do, but in reality, the reason why that never actually matters is simply because of the fact that in linear quantum mechanics, the alpha never really affected how physical evolution happens. It's just a probability statement. So in nonlinear quantum mechanics, if you want to boost these results, what you want to do is somehow actually go into your Hamiltonian and divide by this particular projection operator. But the key point is that the environment, of course, is not local, right? I want to write down local quantum field theories, which means I care about X things of this kind. So what I want to do now is to come up with an operator that measures the environment and projects itself out. But I cannot do that. Then the whole definition of the environment is that it's not local. So there isn't a local quantum field theory operator that I can write down that simply measures the environment and gives me local answers. So it's impossible for me to boost my results in a local quantum field theory. Okay, so this again is not something specific to my theory. Every nonlinear quantum mechanical system will have this feature that essentially you need to allow yourself to do superpositions of very complicated superpositions of the entire universe being in some strange superposition, at which point if you care about psi squared, which you have to because that's your nonlinear term, you then realize that no matter what you do, your results will depend upon what fraction of the universe you are personally in. You cannot boost that in a local way. So in some ways, what we would say is that our framework explains to some extent why quantum mechanics can be linear. It's not because it's fundamentally linear, it's just because of the fact that the universe placed you in this very, very weird superposition, where alpha was extremely small. So this is a very generic feature, in my opinion, of nonlinear quantum mechanics that is going to be local in any way. And the bad news in many ways, or the good news, depending upon your point of view, is that inflationary cosmology naturally places our universe with an incredibly small value of alpha. So if you think about inflationary cosmology, the standard canonical inflationary cosmology, inflation leads to this many, many worlds coming up immediately just through quantum evolution. And inflationary cosmology basically says that my world, what I'm standing right here and giving a talk, is something like e to the minus n of the overall quantum state of the universe. It's incredibly suppressed. Okay? So if inflation actually happened, all of these effects that I talked about go away, canonically small, exponentially small. You can't see it. But does that mean that all of nonlinear quantum mechanics goes away? Interestingly, the answer is no. What we care about in our story, remember, is the expectation value of some field. So this could be a scalar field, it could be a gravitational metric, it could be something of this kind, right? So what is true in something like inflation is that, of course, that is enormous superposition of a very, very large number of very, very complicated universes doing all these kinds of things. And all of Jason's experiment will give you nothing at all, simply because Jason is only 10 to the minus 500 of the universe, okay? Even though Jason's a very special friend of mine, he's still 10 to the minus 500 of the universe, right? But if I want to get a non-zero effect, all I require is there should be some field that has a non-zero expectation value across this entire space-time, and that is only going to be homogeneous fields. There is one field that we know always has a non-zero expectation value, no matter what, and that is the metric operator. The metric is a field that in every universe you'll take in will have a non-zero expectation value. And in fact, in inflation, what you really predict is that all these other universes that you're out there basically have the same common FRW metric, but with somewhat very different perturbations and sort of inhomogeneous. So the various inhomogeneities will average out, but the homogeneous piece will be the same across this entire very complicated state. What does that metric actually do? Because this is now not the standard GR metric, right? I mean, that is there, whatever metric we're used to. There is now this extra contribution coming from this complicated superposition sitting out there. So let us look at this metric, this complicated metric. So essentially, this metric is now interacting with some scalar field or particles, things of this kind, right? The standard thing that we're talking about. And let's look at how this affects the motion of bodies like around some gravitating mass, like the Earth or the Sun, and things like that. So what you do is you take your regular Schwarzschild metric. The Schwarzschild metric tells you how things evolve. And then you look at the expectation value of this metric from the homogeneous piece, from the rest of the universe. So of course, in our world, where I'm standing and I'm creating this matter around me, there is this particular form of the metric over there. And the average value is just this. There is no space, there is no Earth or whatever nearby. So it's just the usual, FRW or really some flat space metric there. So the metric that a particular body near us will respond to is the sum of these two things. It is this metric plus epsilon times that metric. Okay, so you can just compute that sum and figure out what it looks like. What it looks like is basically the statement that the effective metric now, okay, depends upon epsilon. So epsilon hasn't gone away, but effectively it appears as a correction to this RS over R squared term. Okay, so this is effectively a second order correction to general relativity. So it's a weird thing, like, normally I would not have thought that, but what's happening is that because I have this particular metric pollution from the other world coming in, and I'm looking at the motion of test bodies, the actual metric is not just the usual Schwarzschild metric, it is corrected by this amount epsilon at order RS over R squared. Now this is a second order GR correction because RS over R, this term, is a coefficient of GRR. That's your first order GR correction. Now you basically see this as a second order GR correction. So it's very, very small. In the solar system, this is not well tested. Epsilon could be order 1. Okay, it's only now that we're actually beginning to test these kinds of things because we now have probes of strong gravity with things like LIGO. Yes.
So are you implicitly assuming that in all the other branches you're at sort of the same time, like the same scale factor?
Yeah.
Okay. So that could also, like for example, if there were inflation or some kind of eternal inflation, and a lot of the branches were still eternally inflating, that would be a very different.
Very different answer. Yes. My point is that it's very different, but it's non-zero. That's all. So you can basically ask, right, if this kind of nonlinear quantum mechanics is actually correct, this sort of multiverse that people have in mind, this eternal inflation multiverse, would sort of be in some kind of trouble, basically because of the fact that you'd be like, why aren't those other worlds dramatically affecting my metric? Okay. So in strong field tests of general relativity, it's something that we're just beginning to do. This is something that will show up. And it has another very interesting fact, which again, remember, this only shows up prominently in strong field general relativity. So let's look at a black hole, the regular black hole, right? If you look at the normal Schwarzschild geometry for a black hole, the horizon is not a special point, even though there's a coordinate singularity in there. And that is because of the following fact. If I look at the Schwarzschild geometry, the place where GTT vanishes is the same place where GRR diverges. So effectively, that is the reason why the determinant of whatever stays finite, and therefore you just end up getting a coordinate singularity. But now in this case, you take this particular metric, you're going to add epsilon times this other metric. You're going to find that GTT is changed ever so slightly and GRR is changed ever so slightly. What that implies is that now, because of this term, this epsilon in there, the place where this coefficient will vanish, where GTT vanishes, is not going to be the same place where GRR diverges. They're somewhat different. And that basically means at the scale of the horizon, you actually end up getting a singularity. It is what I would call a firewall, right? So it actually solves the black hole information problem by just explicitly telling you, look, GR is wrong, right? It's a statement that is kind of a weird thing where you'd be like, in inflationary cosmology, the standard inflationary cosmology, all of the experiments we do locally in the Earth would tell you quantum mechanics is absolutely linear because these effects completely average down. But if you do a strong field test of general relativity, where RS over R squared is order 1, like, for example, at a black hole, you get dramatic differences. So I'm extremely excited about the possibility of using something like LIGO, for example, to actually test nonlinear quantum mechanics. So with that, let me conclude. What I can tell you is that quantum field theory allows a very natural way to include nonlinear state-dependent time evolution. It's completely causal simply because of the fact that quantum field theory is built upon providing you with causality for entangled distance systems, right? It's not a big surprise that this works. It's exactly what quantum field theory was designed to do. The thing that surprised me the most in this whole story is that these conventional tests of quantum mechanics that we have done in atomic and nuclear systems are totally useless in terms of constraining causal nonlinear theory, simply because people have not worked hard enough to localize the states. Even though none of those tests actually apply, there are pretty straightforward experimental tests one can do that aren't even that expensive to go and test the system, right? And with the caveat being that the cosmological sensitivity means that it may well be the case that all the local experiments give us null results, but the real way to probe it may be in regimes where we are probing strong gravity, for example, with LIGO, things like that. So with that, let me conclude. Thank you.
Are there any questions? Any more questions?
Can you elaborate more how you test this in LIGO? I mean, with LIGO, LIGO has done a number of tests of strong gravity, of GR essentially, right? Is there some of this already?
So they've just begun to do it, right? So if you look at what exactly they're testing, so the tests will be things like essentially they've measured the graviton mass to be very small, things like this, right? But if you're really asking the question here is the statement that when I go very close to the horizon, is the physics exactly what I've described by GR or not? Those things are only tested now at order 1 level, not more than that.
Okay, so you have to essentially look at more
details of the waveforms. Exactly.
May have degeneracy in other kind of.
Exactly.
There was another question.
Yeah.
So when you were talking about cosmological superposition with alpha u.
Yeah.
And you said alpha could be small.
Yeah.
Doesn't the value of alpha depends on the basis you chose? Can you change?
No, it's a state, right? I mean, like the quantum state is whatever it is. So your universe, where basically you are sitting there entangled, blah 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 blah. I mean, you defined it, right? Because you're saying I'm here right now. So the moment you have decided who you are, you have told me what the value of alpha is.
Can I change it from UM basis to another basis? And doesn't that say something different?
Not really, right? Because at the end of the day, you have to define what observable you're looking at, right? So put all of your stuff, right? Your lab, etc. That is not a basis in that is not some weird thing, right? Like you have entangled yourself in this very specific way to create what it is that you mean by your world. So whatever basis choice or rotation you do, obviously if you're entangled in this way, all of that will move together.
Okay.
Right? Yeah. Yes.
You said the theory could be Lorentz invariant, but like in order to define these states, it seems like you've chosen some time slicing.
Oh, so this is the usual thing that when you write down quantum field theory in the Hamiltonian language, it doesn't look manifestly Lorentz invariant, but except of course it is. And in this case, what's really true, I should be more careful about what I said, is a statement that in the vacuum, of course, is Lorentz invariant because the vacuum, I'm not doing anything at all. Once you create a state, obviously the expectation value depends upon the state. So you have broken Lorentz invariance, except all the evolution on top of that is causal. That is a more correct way of saying it.
Okay. Any more questions? I'm not sure if people.
Yeah.
Oh, I see. So they cannot hear them.
No, the chat only has 3 questions in it.
Okay. So,
Okay. Yeah, I think hopefully they actually heard me talk.
yeah, probably.
Yeah.
Now it's looking for questions in the
Yeah, are there any questions in the chat? I'm happy to take them. We can't, yeah, I can't hear you talking, I guess.
No,
This is calling.
that's
Yeah.
Stoicism.
Okay.
Okay.
All right.
Okay.
Right. Well, thank you.
There are no more questions. Well, thanks, Surjeet.